Suppose you're asked to add up 1 plus 2 plus 3 plus 4 plus 5. They will stop at 5. But you want 5 1s and 4 2s and 3 3s and 2 4s and 1 5. In other words, this looks like this. 1 plus 2 plus 3 plus 4 plus 5. 1 plus 2 plus 3 plus 4. 1 plus 2 plus 3. 1 plus 2 plus 1. This is the same as this because, as you can see, you are adding up 5 1s, 4 2s, 3 3s, etc. Now, this comes up frequently. So, let us derive a formula for it. So, basically, we have the summation as I goes from 1 to n, because we want to expand this for any n, or write it for any n. Well, we're clearly going to have I, because I is 1, and then 2, and then 3, and 4, and 5, all the way up to n. Okay, but now what are we multiplying it by? Well, if you notice, if n is 5, these two numbers keep adding up to 6. So the n, so it adds up to always 1 more than n. So you have I, and the question is, what do you add to it to get n plus 1? Well, here's the n plus 1, and I'll take away j. So it's n plus 1 take away, and of course I didn't mean j, I meant I. You take away I, and then you get n plus 1. And you multiply the two. First, let us verify that this is working. When I is 1, this will be n times 1, that's right, plus, so this keeps going down by 1. So when I is 2, you'll get n minus 1 times I, which is 2, and then I gets 1 more. So you're going to take away 1 more. So instead of taking away 1, you take away 2. And that's going to go up 1, etc. Okay, so we have the right summation, n plus 1 minus I times I, and I maintain that this is n times n plus 1 times n plus 2 all over 6. And we're going to prove this. So this here is a fact, and here is the proof. So we have the summation as I goes from 1 to n of n plus 1 minus I times I. Okay, let us distribute that I. I goes from 1 to n. You have ni plus I minus I squared. Okay, now the summation I proved is linear. That is, you can take the summation of each term separately and add and subtract them. I equals 1 to n of the first summation plus the summation of I of the second summation minus the summation of I squared as I goes from 1 to n. Now the nice part is we know all of these. This has nothing to do with I. Well, you know what? Let us even combine the first two. It's the summation as I goes from 1 to n of, well, here you have n i's, and here you're adding 1 i's, so that's n plus 1 i's, minus the summation of I squared. The n plus 1 has nothing to do with the summation, so I can factor it out in front. I goes from 1 to n minus the summation of I squared. So both of these summations we know. N plus 1 times this summation, well, that's n times n plus 1 over 2, minus the summation of I squared as I goes from 1 to n is n times n plus 1 times 2n plus 1 over 6. So the first thing I will do is I will get common denominators by multiplying top and bottom of the first fraction by 3. And when I multiply the 2 by the 3, I get 6. And then I'll say, you know what? This term has a factor of n and another factor of n plus 1. And this has a factor of n and a factor of n plus 1. And I know I can factor out the 6. So I can factor out n times n plus 1. And what goes in the brackets is literally everything that doesn't have an arrow by it. And if I'm going to say that, let me put an arrow by the 6. So, this 3 times the n plus 1, the minus sign, and then the 2n plus 1. Okay, so we have n times n plus 1 over 6 in front. We have 3 n's, and we are taking away 2 n's. So we have n, and we have 3, and we are taking away 1. So we have 2, and in a few seconds, I get to say I'm done. N plus 2 over 6. That is this summation right here. Now, it follows their chain. That's why you have to put equal sign. What I just boxed equals this, which equals this, which equals that, which equals this, which equals all of this, which in turn equals this, which equals this. I know they're equal. I put equal signs, which equals that. Any two of the box things are equal. In particular, the first one equals the last one. That is why we're done. Continue watching the proofs, please.